All right, so let's just do a quick review here now. What we've done up to this point is, well, in last chapter we talked about this to that, right? Elimination. We also talked about substitution, of course, right? Now we're talking about this. First thing we did was we talked about this, right? Then we talked about, we talked about that in several sections. I've forgotten now, uh-oh. Did we talk about that again? Just the opposite, like going back to a halogen? Wow, I don't even remember. I think that hasn't been done yet, right? But then there's a reaction, there's a reaction, right? This is from chapter 7. Here's chapter 8, here's chapter 8. Now what we talked about was going from that to that, right? That was where we just added 2 hydrogens, catalytic hydrogenation. Now we're going to talk about going from this to this, right? This is called halogenation, and we're also going to talk about halohydrin formation. Another reaction, okay? So just an overview. You should be thinking like this all the time. It'll help you pack things away nicely if it's not just a bunch of mumbo jumbo in your head. All right, so we're interested now in halogenation and in halohydrin formation. That's a Y. Halohydrin formation. That is a Y. Okay. Halogenation is the addition of 2 halogens across a double bond, as we see here. Oops. And yeah, halogenation is where we see double bonds across here. An important step in PVC, in the formation of PVC. And it's only practical with chlorine and bromine. So iodine doesn't work for reasons which I have a kind of a funny story about, which I won't tell you now. I'll tell you on request. And halogen and halogenation with fluorine is not practical either. So in terms of Regio selectivity, it goes anti. Yes, this is important. One goes on top, the other goes on bottom, and you'll appreciate why when we look at the mechanism for it. Okay, so bromine, as you would guess, is nonpolar, right? Because the 2 atoms have the same electronegativity. However, since it's so big, it is polarizable. An approach of a nucleophile will induce a dipole, right? So if you get a negative coming over here, then all of a sudden it's going to be pushing the electrons over to the other side, right? This is called an induced dipole. You've seen that before. Think of bromine think of bromine, the molecule, as a bromine atom with a good leaving group, right? Where the leaving group here would be bromide, right? There's bromide. So if you get this nucleophile, which in this entire chapter, the nucleophile is the pi bond, right? Those pi electrons come over here, boom, they induce the electrons away, and these electrons leave, right? So then you end up with the carbocation. Now watch this. This is cool. Now the carbocation doesn't just hang out by itself. We have these electrons over here. Okay. Oh, let me motivate this first. Only anti-addition is observed. So if this was the whole story, then the bromide could go either side. That'd be no big deal, right? Of course, there would be some crowding over here, okay? But it could go on either side. But that's not what happens. And here's why. It's not what happens because, watch this. When these pi electrons come up and attack that bromine and the bromide leaves, right? You see that? Then this other pair of electrons ends up making an association down here, and you actually get, look at this, a 3-membered ring. And I've told you we're not going to see this a lot, but it's important here, and it explains why we only see anti-addition. So we get this 3-membered ring here. This is called a bromonium ion. You should say it. You should say it out loud. You get this bromonium ion, and when you get the bromonium ion, you can see that the bromide can attack from the backside, right? Since you've got that plus right here, both of these carbons are very partially positive, right? They're super nucleophiles. Plus, these electrons are all pulled to the side. So this is like its backside is just hanging out in the breeze, right? To get tagged by this bromide. Okay? So bromide attacks from the backside, as we said in the previous slide, and so you're going to get this plus the enantiomer. If it's chiral, you'll get an enantiomer. All right, so the halogenation is stereospecific. The stereochemistry, the starting alkene, determines the stereochemistry of the product. This is a term we don't use a whole lot, but whatever it is in the beginning, if this is cis in the beginning, we're going to get something very specific here. If this is trans in the beginning, we're going to get a meso compound, right? And that's what stereospecific means. Now, halohydrins are formed in the same way. So they're formed when this is done in water. If this is done in water, then you've got lots of other molecules hanging around, lots of good nucleophiles hanging around. It's actually a weak nucleophile, but if there's a lot of them and this backside is open, right, and it's partially positive, right, this says positive up here, but don't forget, bromine is relatively electronegative and it's positive, right? So it's pulling the electrons off of these. So you definitely have a big partial positive here and a big partial positive here, which makes this a good nucleophile. So if you do this in water, then you're going to get some attack by the water also. Okay? If you do it in water, there are many more water molecules than there are bromide ions. So the water outcompetes for the bromonium ion. All right, after water attacks, it's deprotonated by another water molecule to yield a bromohydrin product or a halohydrin product. All right, and so if you got enough water in there, you're just going to get a proton transfer. No big deal. We've seen this. I think you've seen this 100 times. So look at that right there and say, yeah, I definitely would have predicted that. Okay, and so this is a bromohydrin or halohydrin. This is a chlorohydrin. It's the same thing, same mechanism. Okay, now the halohydrin formation is also regio selective. That is, the halide goes to the less substituted. The halide goes to the less substituted. And to appreciate why, we'll look at the mechanism. So recall that you've got this bromonium intermediate, right? So you've got this bromonium intermediate. Well, it turns out that this is the more, even though that would be like the more open, right? But that is the more partially positive. Okay? And there's the reason why. It's more partially positive. Well, actually, this doesn't actually say why, does it? The regio selectivity from water attacking the substituted carbon, it attacks it faster than it attacks the less substituted, which is essentially what I just said a second ago. The more substituted carbon has more ionic character. That is also what I just said, but that's, I think, the real critical step there. The more substituted has more cationic character, and therefore it's a better electrophile. Okay, so we just now talked about, let me go back up here to the first slide. Where's our first slide? Right? And said in this section what we talked about was addition of a halogen across a double bond. That's I drew this as if it's syn, but it's actually anti, right? We saw that that's anti-addition because of the halonium intermediate, which was typically bromine is the most common one we see. And then also this is also anti-addition. Okay, where this goes on the more substituted. The hydroxyl goes on the more substituted carbon. All right, go practice these. Good luck.